Let us start today's discussion with the collection B. It's the collection of all open intervals in the set of real numbers. You already know what an open interval is. You have two real numbers A and B where A is less than B. This open interval is the set of those real numbers that are greater than A and less than B. It turns out that this collection is a basis for some topology on R, and this topology we will call the standard topology on R. And whenever we treat R as a topological space, without saying anything about the topology, you should assume that in the background, this is the topology that we have, the one generated by this basis. And we denote the space by simply the symbol R. Now let us see how exactly this is a basis. So to prove that our collection B is the basis for some topology, we have to verify two conditions. The first of which is that any real number is contained inside some basis element. So we take any real number x, and obviously it's contained in the open interval x minus 1, x plus 1. And that open interval, of course, is an element of our collection B. So that means we have verified the first condition for a basis. And next we have to go for the second condition, where we take the intersection of two basis elements and then choose a point in, you already know what we are talking about. To verify the second condition for a basis, we take the intersection of two open intervals a, b and c, d in R, and we take a real number x in that intersection. Here our aim is to show that there exists another open interval which contains x and which is itself contained in this intersection as a subset. See, there is no need to write that where a, b, c and d are real numbers and where a is less than b and c is less than d, because you can simply write where these intervals are coming from B. That's enough. Now in search for that third interval, we consider these two real numbers E and F. E is the maximum of the left boundary points A and C, and F is the minimum of the right boundary points B and D. What will these numbers give us? Let us see. First of all, note that x being an element of this open interval satisfies these inequalities, because that's what this open interval means. Similarly, x is also here in the second interval, so we also have x satisfying this second set of inequalities. Now E being the maximum of A and C is either A or C depending on which one is greater. Now no matter what the situation is, whether E is A or C, in both the cases it is less than x. So that means the maximum is less than x. Similarly, the minimum of B and D is either B or D, and in both the cases x is less than the numbers, and that's why x is less than the minimum f. So what do we see from here? From here we see that the two real numbers E and F trap x between them, and that is why x belongs to this open interval E, F. And this is a legitimate open interval, that means it's an element of the collection B. What condition do we need for such an open interval to really be an open interval? Namely, the condition that E is less than F. Note that in showing that x lies between E and F, we have also shown that actually E is less than F. So it's okay to consider this open interval. But now comes the next question. Is this open interval really contained in this intersection? Yes. Let us see how. So we take any point y in E, F. Then y is greater than E and less than F. Y is a real number. And what does this imply? These inequalities imply these further inequalities. You can see that we have simply written those same inequalities here. E is less than y and y is less than f. But then we wrote something extra. A is less than or equal to E. How is that true. What is A? A is one of the numbers whose maximum is E. So see, this E is either A or C. Let us see the two cases that are possible here. One of them is A is greater than or equal to C. In that case, A is equal to E. So we have that option of equality. The other case is that A is less than C. In that case, the maximum is C, right? But then E is equal to C and A is less than C, so A is less than E. So we see that the maximum is greater than or equal to A. Actually, the maximum is greater than or equal to both the numbers. And that's what we used here. E is greater than or equal to both A as well as C. Similarly, the minimum of B and D, which is F, is less than or equal to both B and D. But then what are we getting from these inequalities? The first set of inequalities ultimately tells you that A is less than Y and Y is less than B. Don't forget that this is what the relationship is between A and Y, strict inequality. Similarly, Y is strictly less than B. So that is why Y belongs to the open interval A comma B. Similarly, from the second set of inequalities, we are getting the fact that Y belongs to C comma D, and hence Y belongs to their intersection. So we see that any element Y in this open interval E comma F is in this intersection, and that's how this open interval is contained in the intersection. That's what we need for the second condition for a basis to be true. So we are now done. But actually something more is true. In fact, it turns out, and it's very easy to see. Okay, if you carefully see what went on here, you would quickly realize the fact that this intersection is not just containing this, but in fact is equal to this. Okay. So now we have the fact verified for us, proved for us that yes, indeed that collection of open intervals is a basis for some topology on R, and that topology we are going to call the standard topology on R. Besides this, there are two other topologies on the same set, on the set of real numbers that we will now see. So this is another collection of subsets of R, the collection of all half open intervals of this type, closed on the left side, open on the right side. You can call them closed open intervals if you want. It turns out that this is also a basis for some topology on R. And the verification that this indeed is a basis runs similarly like that previous one. And here also the same thing is true. It's obviously very easy. I mean, you can see that instantly how the first condition for a basis is true. There, do you remember, moments ago we took any arbitrary real number x and we then saw that x belongs to the open interval x minus 1 comma x plus 1. Here, you can consider instead the closed open interval x comma x plus 1. That's it. So that gives you the first condition. For the second condition, you will similarly take two such half open intervals and you take their intersection and choose a point in it. Here also, you will be able to show exactly similarly that the intersection is in fact itself a basis element. That means I should not perhaps say basis element because that's what we are verifying. The intersection of two such intervals which really intersect, which are not disjoint, is again another interval of the same type, just like what we have here. The intersection of two open intervals is itself an open interval. That same fact is true here as well. And there are some other things about this. What shall we call this topology? Let us next see that thing. The topology generated by this new basis B prime is called the lower limit topology. Okay, lower limit topology. And when we treat the space R means the set R with this topology, we would use this symbol for the topological space R suffix L, lower limit topology. And then there is another topology on R, different from these two topologies. To introduce this third topology, we need to first consider the set of the reciprocals of all positive integers. Let us call this set K. Now the collection which we are next going to consider is, let's call it B double prime, B prime prime. Okay. And what are the elements in this collection? The elements are all the open intervals, just like B, but there are other things also. In R, along with all sets of this form, all open intervals again from which the set K has been removed. The open interval A comma B, set difference K. So this B double prime consists of all objects of these two forms. And just like the two other collections B and B prime, this third collection also turns out to be a basis for some topology on R. And the verification that this is a basis again goes similar to the previous two cases. However, verifying the second condition here will really involve many cases, because two types of elements are there in B double prime. So many cases will arise depending on what type of elements you are considering from B double prime and taking their intersection. So it's a little long. I have gone through the details, so if you want you can go through the details, or you take it on faith that yes, it is also a basis for some topology on R. And this topology is called the K-topology on R. And when you consider R as a topological space with this topology, then you denote it by R suffix K, just like RL denotes the space of real numbers with the lower limit topology. Now the next natural question is this: what is the relationship between these spaces? Ordinary R, R with the lower limit topology, and R with K topology. Let's see. This is the relation, lemma 13.4. It states that the topologies of RL and RK, that means the lower limit topology and the K topology on R, are both strictly finer than the standard topology on R, but are not comparable with each other. Let's prove it. Let us start the proof by naming the topologies. Let the topologies on R, RL and RK be tau, tau prime, I wrote double prime here, tau prime and tau double prime respectively. That means this is the standard topology on R, this is the lower limit topology, and this is the K topology. And next what we do, because we have to prove that these two topologies are finer than tau, so we take an arbitrary basis element of tau and take a point x in that basis element. You can then see that this closed open interval x comma b obviously contains x as a point in it, and which is itself contained in a comma b. It's a pretty easy thing to see why we have this containment. And the important thing is that this closed open interval is a basis element in the basis for the lower limit topology. So what does that tell us? It tells us that the lower limit topology is finer than the standard topology. And we are making this conclusion using lemma 13.3, which lets us compare two topologies which are given by bases. So that's how the lower limit topology is finer than the standard topology. And to see how the K topology is finer than the standard topology is even easier. Why? Because this basis element that you have in the basis of the standard topology is actually also a basis element in the K topology. Recall that this basis consists of all ordinary open intervals and open intervals difference K. So that's why you can think of this itself as an element of B double prime, such that it contains that point and is contained in itself, which was the original chosen basis element of the old basis. So again, by this same lemma, the K topology is also finer than the standard topology. But we have to show that these containments are strict, that is, these are strictly finer than the standard topology. To show that strict containment, what you do this time, you take a basis element of the lower limit topology, that means tau prime. Say this basis element, closed open interval, closed 0, open 1, and you concentrate on the point 0 from this. Okay. Now there exists no basis element of the standard topology, which is an ordinary open interval which contains this 0 and is itself contained in this open interval. Why? Because any open interval which contains 0 has negative real numbers as well. But then how can it be contained in this? All of whose elements are non-negative real numbers. And that is why by that same lemma, because the two parts of the lemma, two parts means the two statements are logically equivalent. So if one of them is true, the other one is also true, and if one of them is false, then the other one is also false. So by that lemma, the standard topology is not finer than the lower limit topology. And that is why combining this with this, well, not this but this, you get this strict containment, that the lower limit topology is strictly finer than the standard topology. Okay, and what about the K topology? Consider this basis element for the K topology, the open interval -1, 1 from which that set K has been removed. That means all the reciprocals of positive integers have been removed. And concentrate on the point 0, which obviously is in this basis element. 0 belongs to this, and since 0 does not belong to K, so 0 will belong to this difference set as well. Now again, there is no ordinary open interval which contains 0 within it and which is entirely contained in this set. What is the reason? The reason is that the reciprocals of positive integers form a sequence which converges to 0. So no matter how small an open interval you choose here, which contains 0, it is bound to contain reciprocals of positive integers. Actually, it will contain almost every reciprocal, only finitely many will lie outside. So if those reciprocals are inside this, but no such reciprocal is here because they have been removed, how can this be contained in this? It's not possible. So that is why, again, by that lemma, the standard topology is not finer than the K topology. And that is why the standard topology is strictly coarser than the K topology, or that the K topology is strictly finer than the standard topology. And finally, we have to also show that the K topology and lower limit topology are not comparable. So next, let's see that. So we again considered that basis element that we considered moments ago of the lower limit topology, closed open interval 0, 1. Now this time we focus on the K topology. Standard topology, that thing is over. Okay, we saw whatever we had to see about that. So there is no basis element in the K topology either of this form or this form that contains 0 within it as a point and is itself contained in this. But why? Let us first consider an open interval. Okay, actually this we already saw, no? If any such open interval contains 0, then automatically it contains negative real numbers, because there is a room on the left side of 0 within this interval. But this one does not have any negative real numbers, so no such thing can be contained in this if it contains 0. What about these other somewhat more complicated basis elements? Open intervals from which reciprocals of positive integers have been removed? Well, the reciprocals lie on the positive side of the x-axis, that is, they lie on this side of 0. So whether they are being removed or not, that does not affect the fact that if any such interval contains 0, then it is containing negative real numbers as well. Note that removing or not removing reciprocals of positive integers does not affect the fact that there are negative real numbers here also, if they contain the point 0 within them. And that is why no such basis element can itself be entirely contained in this. So then what is our conclusion? And finally we consider this basis element of the K topology, which we considered previously also. From the open interval -1, 1, the set of all reciprocals of positive integers has been removed. Now there exists no basis element in the lower limit topology, which of course is of this form, which contains 0 and is itself contained in B. Now what is the reason? What is the reason for this to not be a subset of B? Well, note that if any such interval contains 0 within it, then there is a little room to the right of 0, no matter how small, and that little room contains infinitely many elements of K, because the reciprocals of positive integers again form a sequence that converges to 0. In fact, almost everything of the sequence will lie in that little area. So then how can such an interval be contained in B which does not have any such reciprocal? And that is why, again by lemma 13.3, this time the lower limit topology is not finer than the K topology. So combining these two non-containments, you conclude that these two topologies are not comparable. Each one has at least one open set which is not there in the other. So none of them is bigger or smaller. They are simply not comparable. I should say finer or coarser. So that is the proof of this result. And there is one more thing in this section, namely the notion of sub-basis. We have seen that due to the vastness of the topologies that we are working with, we needed the notion of basis. We cannot specify all the open sets. In most of the cases it's impossible because the topology itself is extremely large. But of course, we can express a topology or generate a topology using a smaller subcollection which we are calling basis. Now we can simplify it even more and give an even smaller subcollection that we will see will be called subbasis. That however we will do next week. So see you next week on the same day with the notion of subbasis. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.